Here's today's wake-up question. Here's a hexagon. Can you draw 3 line segments to turn a hexagon into a cube? Think about it a second. How can I draw a 2-dimensional plane figure into a 3-dimensional figure, huh? 1, 2, 3. There we go. Well, that's enough for a starter today, huh? Today we're going to talk about coordinate transformations, and if only things were so easy going between 2 and 3 dimensions in coordinate transformations, we're going to almost stick entirely to 2 dimensions here, because even though the 3-dimensional formula is straightforward, it gets so much more complicated to write it down that I'm not going to do a whole example on it, and indeed there isn't any in the homework set either in 3 dimensions. But I want you to see the formula. It'll be just like this, just about 3 times as complicated on each problem. Well, here's what we're going to do for coordinate transformations. We've already found that if we did things like switch to polar coordinates when there's a radial symmetry, our integrals got a lot easier, right? What if there's some sort of a parabolic symmetry or some sort of other symmetry, hyperbolic symmetry, who knows? Maybe I can change the coordinates that'll make those problems easier if the boundaries of my figure are a hyperbola. I mean, here's the kind of case we had before. Suppose we had this little region here, and we wanted to integrate over that in xy space, and you take this big sector here, big slice of pizza, minus this little slice of pizza, and this region is what's left. That's really difficult to integrate in xy coordinates, right? You got to start, x goes from in, and then it goes to here, and you got to put this curve on bottom and this curve on top. Then you got to go from here to here with this curve on bottom and this one on top, and then from here to here with this curve on bottom and this one on top, and it's just a mess. So if I want to do an integral, it would be easier to change it over to polar coordinates. Where in polar coordinates, this is r equals some radius 1, and this is r equals some radius 2, and r goes between 2 constant radii. Right? Maybe this is r on the u-axis, r1 to r2, and then theta goes between this angle and this angle, so theta goes between 2 constants. If you transform this to polar coordinates, it's just a rectangle, r going between 2 fixed values and theta going between 2 fixed values. That's a lot easier to integrate between constant endpoints than break it up into a lot of pieces and have non-constant endpoints, right? So that's the point of this section is, could you do this for arbitrary coordinate systems like we did for polar coordinates? So we'll say a map, which is just a fancy term for a function, phi from a, get some things up here, from a plane region in UV space into a plane region in XY space can be used to do a transformation of coordinates. We can change from XY coordinates to UV coordinates. We usually draw the function this way from the UV coordinates to the XY coordinates, even though our integral starts in XY ideally. So if we make a function, phi of UV, that outputs 2 components, u and v, a function of u and v and a function of u and v. We can think of x equals this number and y equals this number, a change of coordinates from uv to xy. And look, if you identify u with r and v with theta, this is r cosine theta, r sine theta. This is the polar coordinates transformation. We'll say more generally we have 2 new coordinates, u and v. But if we do, as a prototype, the polar coordinates example, then phi, the transformation of variables, is x equals u cosine v, y equals u sine v, and I wrote it that way here. This is another way of writing this map. All right. Here's a simple example that's not polar coordinates. This is actually phi of uv equals u plus v, u minus v. You put in 2 numbers, u and v, a coordinate pair in uv space, a point here. Phi is a map that takes you to a point in xy space. It takes you to the point u plus v, u minus v. And we say that the image of the whole space D here in UV space is this phi of D over here. I wrote phi of D. You'll see this in the notes. I'm posting them online. So what is happening here, if we want to find the image under this map, this change of coordinates, what happens to the u-axis and the v-axis, right? Like right here, the u-axis was r, and so that was if you let r vary and hold theta fixed at 0, then you're moving along like this, right? Because theta is 0, And so that's the map up there. What happens similarly here? Well, the u-axis is v equals 0, so I just put v equals 0 in here and I get xy, right, this is x and this is y, is u. Oh, that's just a parametric curve. X and y are functions of one variable u. X equals u and y equals u. You can substitute that in and find out that y equals x, right? So this is parametric equations. When you put v equals 0, you get parametric equations for the line y equals x. There it is. This is the image, we say, of the u-axis. In other words, if you took your map phi down here, it would take the u-axis to this line. How about the v-axis? What's its image? Well, the v-axis is all points with u equals 0. Well, those are the points with u equals 0. You get v minus v. Well, if x is v and y is minus v, you solve for y in terms of x and get y equals minus x. Then the v-axis maps to this line. And so what you've done is you actually just turned your coordinates from the uv space, turned u up this way and v up this way, and it's a rotation actually. Now I want to make a note. That particular transformation is a nice example of what's called a linear transformation. In general, if you take x and y, or phi of uv, to be au plus bv, where a and b are constants, cu plus dv, so constant times u plus constant times v for each coordinate, that's called a linear transformation of coordinates. And generally we want to pick ad minus bc not to be 0. We'll say why later. If you do a linear transformation, a line in uv space maps to a line in xy space and vice versa. And furthermore, parallel lines map to parallel lines so that parallelograms map to parallelograms under this image. If you have here's a rectangle here, that's a special case of a parallelogram. If you take this map we just gave and you take these line segments, it turns out you get this parallelogram over here. So the parallelogram in uv space goes to a parallelogram in xy space. Under the map we put up above, phi uv equals u plus v, that's x, and u minus v, that's y. How do we figure that out quickly? It's not so easy as the x-axis, but what we can do is this. We know it takes lines to lines and line segments to line segments, actually. All I have to do is find these 4 corner points where they map over here and draw straight lines between them. I've got it, because it will also map the inside to the inside, or the outside to the outside, whichever you have. So I take 0, 0, and actually a linear transformation always maps 0, 0 to 0, 0, right? You put in 0 for u and v, you get x and y or 0. So that goes to 0, 0. But the point here, 2, 0, if you put it in 2 for u and 0 for v, you get to point 2, 2. That's this one here. So this point here maps to this one. And then the point 2, 1, under this function phi, goes to, let's see, 2 plus 1 is 3, 2 minus 1 is 1. So that goes to 3, 1 right here. So this one maps to this one, and then this one maps to this one. And so what you find out is that this rectangle in uv space under this linear map maps to this parallelogram over here. Now you might say, how about the reverse question? You know, like if I've actually got this region of integration, how do I find what it maps to going this way? Well, you just have to solve the equations, right? X is equal to u plus v, and y is equal to u minus v in this map, excuse me. So you just write u plus v equals the x coordinate, u minus v equals the y coordinate, and lo and behold, you get 2 linear equations and 2 unknowns. If you have matrix algebra before, this is absolutely trivial by Gaussian elimination. Even if you haven't had it, right, you know how to solve these things. You can solve for one of these in terms of the other and substitute in, or what a lot of people like to do is elimination. They'll add a multiple of one row, one equation, to the other equation. Like here, if I just add 1 times this one to 1 times this one, the v's will cancel, and now I've got 2u equals 6. So you add a multiple one equation to the other to eliminate a variable, hence the name elimination. In this case, I get 2u equals 6, so I infer u equals 3. Put that into either equation and put it in the first one. 3 plus v is 2, v must be minus 1. So I have the point 3 minus 1 is the point that maps to the point 2, 4 in xy space. So I can go backwards. When can I go backwards? You can't always, it turns out. What you want to look at to see if it can go backwards is the Jacobian. If you have a function that maps UV space into XY space, phi, and so x is a function of u and v, y is a function of u and v, like we've been writing. The Jacobian is given this notation, j of phi, or the book even makes it worse than that, JAC of G of P or something. A lot of people just put J. But the Jacobian also has this notation, dxy duv, and this means the determinant with dx du, dx dv, dy du, dy dv, x and y, x in the first row, y in the second, u in the first column, v in the second column. And that determinant is this times this minus this times this, so actually the Jacobian comes out to be this function. And provided you have continuously differentiable functions, functions having one continuous derivative, then you can say something nice about the Jacobian. If the Jacobian is of one sign on a whole open region, then this transformation is invertible. It's one-to-one and onto, we say. In other words, it puts a one-to-one correspondence between the points in UV space and the points in XY space. If you go this way, you go back because there's a one-to-one correspondence between the two. And so you can do what we did in the last example. Well, when can we do that with a linear transformation? Well, actually, let's look at the one we had last example. The claim is on the theorem that we need the Jacobian to be of one sign, positive or negative, never equal to 0. And in this case, for x equals u plus v and y equals u minus v, that transformation of coordinates, I can add these two equations together to eliminate v and get 2u equals x plus y, solve for u, and I get u is 1 half x plus 1 half y. Then I can subtract the coordinates to eliminate u and get that 2v is x minus y, dividing by 2v is a half x minus a half y. So you can solve for x and y from these two equations and two unknowns, provided you got Jacobian not equal to 0. So now I have the inverse map. The map that goes back from xy space to uv space is phi inverse of xy, we usually write. This minus 1 doesn't mean 1 over, it means the inverse function, like logarithm is the inverse of the exponential. Right? U is 1 half x plus 1 half y, v is 1 half x minus 1 half y. It takes your xy coordinates to uv coordinates. And it works because the Jacobian was negative 2, right? It was, if you compute it, right? Partial u plus v with respect to u. This is x. dx du, dx dv, dy du, dy dv. Where x is u plus v. And let's see, did I go this backwards from the way? I wrote this backwards. It's supposed to be transposed this way. It comes out to be the same number. It doesn't matter if you transpose it. This should be u plus v, u plus v, minus v, minus v. It comes out to be the same. Amazed I did that. Alright, so this should be dx du, dx dv, dy du, dy dv. And then you get the same matrix here, 1, 1, 1, minus 1. And it comes out to be this times this, minus this times this is negative 2. The Jacobian here for a linear transformation is constant. In this case, it's minus 2. And since it's not 0, this is invertible. That's why we said at the beginning you want AD minus BC to be non-zero for a linear transformation. X equals AU plus BV, y equals CU plus DV. For those linear transformations, your Jacobian will be A, B, C, D, and that determinant will be 0 if AD minus BC is 0. And then what happens is it'll map the plane into a line or something like that, and you won't be able to do an inverse transformation because it doesn't map the plane to the plane. Alright, so anyway, it worked because the Jacobian wasn't 0. We could find an inverse transformation here. Here it is for general linear transformations. X is AU plus BV, y is CU plus DV. The Jacobian, if you take dx du, dx dv, that should have been, I wrote this backwards again. It must be late at night. That's after midnight. I have to do a stand-up comic routine again, I guess. Lots of mistakes. B and D. Anyway, so I think A, B, C, D, the way I wrote it before for the Jacobian. It comes out to be the same if you transpose this, but anyway. The convention is put X in the first row and X and Y in the rows and columns, and U and V in the, X and Y in the rows and U and V in the columns. Anyway, it comes out to be AD minus BC. So we'll be able to do an inverse if and only if AD minus BC isn't 0. Now here's an interesting thing about these linear transformations. These are the most important ones for us because actually in truth, if you get any kind of transformation that's very complicated, you'll see when we try to evaluate integrals with it, it gets too hard. So linear transformations are nice. Sometimes they'll take something like this. Suppose I want to integrate over this region. What a mess. I got to break it up into pieces, and I've got to write y as a function of x. I could do a linear transformation, take this parallelogram to this one that's a rectangle, actually a square, and it would be easier to integrate in UV space. That's the idea. So these linear transformations are nice for that. Here's an interesting fact. If you work it out, we won't go through the equations, it's simple geometry, but it turns out that the area of the image, phi of p in xy space, is equal to the area of the image in UV space multiplied by the absolute value of the Jacobian. In other words, the Jacobian is the magnification factor. When you take a region in UV space and map it into xy space, this one will be the absolute value of the Jacobian times as big as this one. In this case, since the Jacobian was minus 2, the multiplication factor is 2. This square is exactly twice the area. It is a square tilted as a diamond. Is exactly twice the area of that square. Here's an interesting thing for other coordinate systems, though. J is generally variable, right, for a nonlinear transformation. For instance, for polar coordinates, if I put, what's the Jacobian for polar coordinates? Where phi is r cosine theta, r sine theta. I'll use r and theta instead of u and v. Here's the x dr, dx d theta, dy dr, dy d theta. Put them in the right order this time. And you get cosine theta here, r minus r sine theta, derivative of r sine theta with respect to r, treating theta as a constant, sine theta, derivative of r sine theta is r cosine theta. This times this is r cosine squared, minus this times this is plus r sine squared. Oh, that's just r times cosine squared plus sine squared by trigonometry, that's r, right? That's familiar, right? That r, where did we see that before? It was in our polar coordinate transformation law. It was that the double integral of f of x, y in rectangular coordinates could be rewritten as the double integral in polar coordinates, replacing x with r cosine theta, y with r sine theta, instead of dx dy, put r dr d theta. That's the absolute value of the Jacobian there, actually the Jacobian. We have derived, we have seen that this is actually the Jacobian that goes in here in that example. There's this major theorem here now. This is the big purpose of the Jacobian for us, major concept 2. If phi is a continuously differentiable mapping, a C1 mapping we call it, from the interior of a region D0 in UV space onto the interior D in XY space with J of phi of one sign, not 0 anywhere. Then for f of xy continuous, your double integral in xy space is equal to the integral with x and y replaced by their functions of u and v in the coordinate transformation, and replace the x dy with the absolute value of the Jacobian. This is not a determinant here, that's absolute value. Unfortunately, we've got both of them in the section, you have to figure out which one it is. But the absolute value of the Jacobian times du dv, and what you're thinking of is actually, this is the magnification factor. If you rewrite the limit of the sum of little rectangles here as the limit of the sum of little parallelograms here, this is the magnification factor for each little parallelogram at each point. Even though it's variable, it tells you point by point how to magnify it, and this adds up to this in the limit. So you can evaluate it like this, and in fact in polar coordinates, this was r, this is a generalization of what we did. We can now apply this to other coordinate systems, not just polar coordinates. We know exactly the factor to stick there if we want to switch to hyperbolic coordinates or something. Here's an example down here. I hope you can read it. that's kind of small, isn't it? I wonder if I can magnify that a little. Uh-oh. Maybe not a little. There we go. Suppose I want to compute the double integral of x plus y dA, where d is the parallelogram. Oh, we have to make this smaller. This parallelogram is diamond, if you will, with these corners, 0, 0, 1, 1, 2, 0, 1, minus 1. This one that we saw before, it's the same example. How can I evaluate a double integral of x plus y over this diamond more easily? I can do exactly the coordinate change I showed before that transforms it back into a square. We first did a rectangle, the second example we did a square. This diamond is transformed into this little square here in our recent example. And we had Jacobian was minus 2. So what we do is we say the double integral in xy space, x plus y dA, is equal to the double integral over d0, this region, in uv space, of 2u times the absolute value of the Jacobian, absolute value minus 2, du dv. Well, that means I have to integrate 4u with u and v going between these limits, 0, 1, 0, 1. How easy. I just come out with a short calculation with 2 for that one. So there's an example of actually using it. You can try the homework problems now. Oops, I gotta shrink this down, I think, before we move. Oh, it's the other way, this way. Shoot. Always got to leave time for comic relief at the end here. There we go. Oops. Huh. Oh. Click it too fast, it helps you, unfortunately. I hate it when machines help me. This carries over to higher dimensions. This is a major point I said at the beginning. There aren't problems on this, but you have to see it, right? If you want Jacobian in 3 dimensions, x, y, v to u, v, w, you want to know when is this an invertible transformation and when can I apply a similar integral theorem? Is this, you make the Jacobian d x, y, z, d, u, v, w, and I should have written out what that was, means the determinant dx, du, dx, dx dv, dx, dw, dy du, dy dv, dy dw, I should have written that in the notes, huh? dz du, dz dv, dz dw, and now it's a 3 by 3 determinant. That thing is in general horrible, and we don't want to do too many problems like that. But if you did it in spherical coordinates, you'd find out the Jacobian is rho squared sine phi and verify our coordinate transformation for spherical coordinates, for instance. Good luck, try the problems out. Let me know if you have questions.